Hey, I guess you knew this was coming. We've defined these new circular functions, and now we want to look at the graphs of them. And as I mentioned before, although they are technically not trigonometric functions, they're defined on the unit circle here, we are going to call them in a generic way trig functions because they involve the same words, sine, cos and tan. The important difference, of course, is that now we will go past 90 degrees in a right angle triangle and be able to define sine, cos and tan of angles as large as we like by going around and around the unit circle. Interesting stuff, very important in modelling periodic behaviour like we looked at in the last unit there, the last presentation. And here's some graphs, interesting graphs here. Let's go and get into this and see what you think about graphs of circular functions or trig functions if you wish. Just remember what we're doing. We have an idea where we're mapping any number on as an arc here, and because it is a unit circle, the measure of the angle theta there in degrees is equal to arc length over radius. So we can think of a theta or as a t in there. Okay, get flexible with this stuff as a theta or a t. And remember our new definition, if this is the point travelling around the unit circle, that's at the end of that arc, terminating arc here, the cos here is the x coordinate and the y of that angle is the sine, or the sine is the y. So that's our new definition. We can keep doing this for all size angles, and we could do it for more than 360 degrees, more than 2 pi. That's our idea here. Can you see, therefore, once you've done one circle's worth, one circle, or equivalent to what? 2 pi radians, or equivalent to 360 degrees, we're going to start to repeat the x and y values, all in the same order again. We're going to start to repeat them. And so this is going to give rise to a graph which is going to repeat itself, or when something repeats itself in exactly the same way over and over again, it's said to be periodic. So we're going to look at that. Okay, let's come on down and have a look at what we're supposed to know so far. If you remember from the last presentation, we are trying to remember these values, these key values of these angles, pi and 6, pi and 4, all of those. Now generally we don't memorise the tan. We can work that out from sine over cos if we know those. And here they all are up here, and you really do need, the IB's got a big emphasis on this, we really do need to memorise those for any tests and exams. So what we might do now is just do that all in red and say, hey, you do need to know this along here. I think Pearson's puts it the other way up, with the angles downwards and the sine, cos and tan across. Doesn't matter. I'm again taking screen clippings here from Pearson's. I think this presentation like this is easier to understand as you increase the angle there along the x-axis, what sine and cos going to do. And the common ones there, if we took this here, there's pi on 6, which in a unit circle means that's the arc length, or you can think of it as the angle in radians, or you can think of it as 30 degrees. Be flexible, be able to go between degrees and radians, particularly easy in a unit circle, because remember the measure of angle theta in radians is arc over radius, and in a unit circle that'll be 1. So the measure of the angle theta is equivalent to the length of the arc. Okay, let's move on. And we've got t here, remember from before, sine of t and cos of t. That was to distinguish it between the arc length or the angle in radians and the x's and y's here. and the x value and the y value. So if we put sine x, that gets confusing because it's the sine of this stuff down here, different from the x and y value here. So we're going to clarify that in this presentation. Come on down and let's try and draw some graphs using those values. Here we are. Let's draw the graph of sine. So the sine graph, what we're trying to do is to measure the y value here of points going around. So you're going to start off low at 0 here, 0. As we go up, going to have a maximum when we get over here at 90 or pi on 2. So we've done that much of the circle there, going around, and then into the second quadrant, coming down here. Are you with me here? We're going to go from the maximum of 1 for y, smaller y's coming across, read them across, down to 0. So when we get around a half circle, 180 degrees worth, equivalent to pi arc, remember that equivalence, 180 degrees of revolution is equivalent to pi radians, arc length over radius. And then we're going to go into negative land here. And so we're watching it coming along here, coming along and going down to, what is it here? Once it gets right around here, it's 3 pi on 2, 1/2 worth of the circle, or 270 degrees if you wish, and it's going to be a minimum. It's going to be down at a y value of -1. Then it's going to come back up and finish at 2 pi, back up here, where the y depth, if you like, or the y measurement is 0. What's going to happen next, do you think? Well, with circular functions, this is the important difference between the word circular functions and trig functions. Trig functions stop within a right angle triangle, basically. Trigon, remember, triangle, metric, measurement, triangle measurement. Circular functions is expanding that notion consistently, but it's expanding. So we could actually keep going, couldn't we? Around and around the circle, bigger and bigger, lots of the arc length. So it looks like this function is going to repeat itself every 2 pi, or have a period equal to 2 pi. This is mapping sine, the y value that you get with the point going around here. The y value of the point on the unit circle is the sine of t. Keeping this idea here of being t separate from x. Quite often later on, once we get out of the unit circle, if we draw the graph of y equals sine x, we will mean the variable here is going to be called x. We're not using x here because we don't want to confuse the the domain expression for sine with the x's and y's going around here. See this? So y is the sine of t. X is the cos of t. Separating them. Do you get it? Let's go on and have a look at this mapping. So this is something you saw before with the Ferris wheel, with modelling. And so we said here, as we go up, this is about 30, 60, etc. Here are our numbers. 30, maybe that's 60, that was 45. All the different values, these are the y plots. So then we go around. See here that we've gone back to x, the sine of x, where x is the angle. Stayed in angles here, in degrees here. Degrees. Is this going to be useful if this is modelling the behaviour of the Ferris wheel? I don't think so. We're going to need actual arc lengths here in radians usually. Convert to radians because we are measuring a position, if you like, going around here, an arc length. We're interested in more here, not the angle at the centre. So we will choose this as pi on 2 and so on as we model, if we're going to use this in a practical description of what's happening on a Ferris wheel and so on. So it's all getting consistent. Interesting, this idea of ups and downs here, and the function is clearly going to repeat itself. Does the Ferris wheel keep going around and around? Yes, as long as somebody doesn't turn the power off the motor and you get stuck up the top. Uh-oh, that wouldn't be good. Let's keep going and have a look at this time cosine. What's the difference? Well, what we're going to do is start at 0 again here with no arc length, and then we'll gradually go along the arc, and this time the cosine is the x value. So where do we start? The x value at 0 here, 0 arc length, is 1. That starts at its max. And then as you come along here, the x values are decreasing. The ones I'm using here, what's this? 30 degrees, because the cos of 30 degrees, or pi on 6 equals root 3 on 2. I hope you've memorised that. And then this is cos of pi on 3, or 60 degrees, is a half, and so on. And so when you get up to pi on 2, the x value has actually gone to 0. So it's a little bit different here from sine. And if we keep going, the x values in this region go this way. They're negative. And so the graph over here for the next half a circle, all through this here, they are negative x values. So it's all below the axis. And what is the lowest it goes? Goes to neg 1 here at pi. So its max occurs at 0, and its min occurs at pi, and the min is neg 1, the max is 1. So we're starting to see some interesting results here. And then, of course, comes back to at 3 pi and 2, we've gone around to here, the x value, just scrub that out there, the x value is 0 there. And then we finish off when we're back at 2 pi, the x value is 1. And that's going to be periodic as well. The same period of 2 pi. Period is equal to 2 pi there. So that's very, very interesting, the patterns we're seeing here. The cyclic or periodic behaviour. Another way of saying it is cyclic. It's cycling. And in subjects like physics, you'll probably see that language more than periodic. Let's go down and compare them now of what we've found. Well, sin x is up here. We're going back to using x as the function's domain variable, what it operates on, because we're coming off of the unit circle now, and saying as we change this either in degrees or arc length over radians, what's true? Well, the first max, here's the max statement, the first max in sine is at that pi and 2 mark. And then it's going to repeat itself every time you go around a whole circle's worth. So this is every 2 pi. So this is back around a whole circle again. You're going to get a repeat. As long as you go around a whole number of circles worth, whole number z. And you can go positively for the angle, that's anti-clockwise, or negatively. Still going to repeat itself as you come back to that position. All right, what about the min? The min is at neg pi and 2, or at, I suppose you could say here, 3 pi and 2. By convention, if we go past pi, by convention, we usually write this bottom half of the circle as negative. So that's pi to there and neg pi to there. But you could call this point around here positive 3 pi and 2. That's another way of doing it, because that's what we're doing here. And it would be down to a minimum. So when is it a minimum? When the value of x is neg pi and 2, or any addition of a whole number of multiples of 2 pi. Okay, what about cosine? That's a bit different. It starts off at 0 being its max. And then 2 pi later, it will be up there again. So the same thing. Travel a whole circle's worth around, and you'll be back to that point, either positively or negatively. So this is a whole number lots of 2 pi to get you a circle's worth back. And then, of course, it had a minimum at x is pi, or neg pi if you wish. Over at neg pi, it'll be a minimum as well. So we could write the same expression same type of expression for the minimum. So are you seeing that the period of both of these functions is 2 pi, or 1 circle's worth, if you like? Okay, let's keep going. Let's go down and look at some of the interesting properties of these two next to each other. All right, well, I want to do cosine first, because there's something obvious. Look at this side, look at this side. Look at it, look at it. Uh-oh, it's symmetrical about the y-axis. Symmetrical about the y-axis. What does that mean? Well, what that means is the function value in x is the same as the function value in neg x. Do you remember that? If you put in neg x, you're reflecting the graph in the y-axis. And these are identical here. See the identical pattern. So the function cosine, when you do cos of x, it gives the same value as when you put cos of neg x. What about sine? Hey, that's a bit different. Come across here, the sine of neg x is all down there. It's a negative. So here we've got the pattern. The function value in neg x is minus the function value in x. Or sine of negative x, reflection in the y-axis, is equal to minus the sine of the original function here. So a function that behaves like that is called an odd function, because we have, if you like, diagonal symmetry about that O point, where the function is symmetrical about the y-axis is called an even function. Okay, so sine is an odd function and cosine is an even function. Just something interesting enough. Not strictly in the course to know about odd and even functions. Okay, let's move them. You knew this was going to happen. Graphs of transformations. Transformations is a very important area in this course. We've done transformations of lots of functions so far. X squared, y equals e to the x, y equals ln x. And here's a summary, a nice summary here from Pearson's textbook on the effect of various transformations on the formula. So if you add d to a function value, that's a translation of d units. If d is positive, it's up. If d is negative, it's down. What about changing the x value before the function operates on it? If it's plus c, then it moves left, remember, in the opposite direction to the sign of the constant. If c is a negative, it moves right, the opposite direction to the sign of the constant in that x translation. Opposite direction to the sign of the constant in there. Opposite. Okay. Reflecting in the x-axis, you multiply the function by negative. If you are reflecting in the y-axis, I'll go down to this one next, then you put in neg x in place of x in the function. If you multiply the whole function by a number out the front, it's a vertical stretch. Here we generally say you don't usually use shrink. It's still a stretch with a scale factor of 1 on a. Okay, if a is greater than 1. If it's a fraction, it's a shrink of, it's a stretch of a fractional value. Always use a fraction rather than saying a shrink. It's a shrink of a factor a, if a is a fraction, but it's better to say it's a stretch of 1 on a. Okay, a stretch of that fraction. Okay, f times b of x, what's happened? You've multiplied the x value by a constant before putting it into there. It's a stretch. Okay, and if b is a number which is a fraction here, it's a stretch of scale factor b. Factor b. So if it's a half, then you actually stretched it by twice that. If it's a number basically bigger than 1, like 2x, you call it a stretch of 1 on 2. Okay, so just got to watch that there. It's really a shrink of a factor of 2 there. I disagree with that. Here, when it's a shrink and b is greater than 1, like 2, we're shrinking it by a factor of 2 or stretching it by a factor of a half. Just be careful with your language there. I prefer, with the IB, it prefers using a stretch in both of those. If the number's bigger than 1 in the X stretching, it's actually stretching by a factor of a half. We'll look at that again later on. It's a bit of revision needed there. Okay, come on down, and here they are all done to sine and cos, and this is what this unit's going to be about now. So we go in here and we see it's a stretch of a factor b. We'll have to be careful what value b takes. Then it's a translation, opposite sign to that. Then we will maybe here next think of it as a stretch in the y direction, and then translate it all up d, or depends on the sign of d, doesn't it? And cos the same thing. We can do some sort of stretch in the x direction, then translate it in the x direction, then translate it in the y or whatever. We usually would do the stretches first here. Makes it easier to watch what we're doing with the function. Stretch it in the y by multiplying by that a value. It could be a stretch or a shrink, depending upon. We'll get rid of that stretch, the shrink, sorry. We'll talk about a stretch with a scale factor 2 or a stretch of a scale factor a half, which would be effectively a shrink. And then your y translation. So that's what we're going to do. We're going to pull apart these functions and see what translations are involved. Okay, are you ready? Here's some exercises here from Pearson's. Let's have a look. Sketch the graph of each function from neg pi to 3 pi. So what's 2 cos x likely to do? Well, let's have a look at cos x. Draw that first from before, from neg pi around to 3 pi. And plotting the values, cos x looks like this one. So what's 2 going to do? It's going to stretch it by a factor of 2 in the y direction. So it's a stretch in the y direction of a factor of 2. Every value is going to be doubled now. Okay, you do the key points is the best way to go. But actually they're all doubled, all these. But it's important to take the key points and double them. So the negatives get twice as negative, the positives get twice as positive. Okay, do you get it? Same as x squared, 2x squared, and so on. Let's look at the graph of cos x plus 3. There's cos x. Let's draw it. Here it is down here. Plus 3, adding to f of x a constant. This is the form here, f of x plus d. So what is that? That's a y translation. Translation in the y direction. So our mean position, I might call this line that has some symmetry of sine and cos about it, you can call that the mean position, because there's oscillation or displacement above and below. So the mean position is no longer y is equal to 0, it's been moved up to y is equal to 3. Okay, let's go down and have a look at part C. What about the graph of 2 cos x plus 3? That's a combo. It's combining both of them. So what will you do first? Well, hang on, let's just go up here. What will you do first? Well, let's do a vertical stretch of a factor 2. So there's cos x. Stretching it will be what we had before. It's like this. 2 doesn't stretch. 0 doesn't stretch. When a value of the function is 0 there, when you double 0 you still get that. But when you double this, you're down here. So we're going to stretch it, and the mean position is still the x-axis. So then we're going to take it up to 3. So now, doing this y translation, so now the function has a mean position of y equals 3, or an axis there of symmetry, and the function will go 2 above it, because it's 2 cos x, and 2 below it. Okay, so that's actually called the amplitude. We'll come on to that in a minute. The maximum deviation from the mean position, 2 above and 2 below. So it's called the amplitude of the oscillation. How far above and below the mean position in a symmetrical way do sine and cos go? Let's keep going. Let's do a half sine x take 2. Well, maybe do the shrinking first of all. The stretch by a factor of a half. That's what the IB prefer. It's always a stretch by a scale factor of a fraction, which is equivalent to shrinking, if you like. But we don't say that generally. I don't like that. Okay, there's sine x. Let's do a half sine x, because that's going to reduce its amplitude. Shall I do that in here? I think I'll do that in here. Can you see what I'm doing? Half of the amplitude, just keeping in mind when the function has a 0 value, that doesn't move. The half 0 is still 0. So we do that, and then we're going to translate it neg 2 in the y direction. So the mean position becomes y equals neg 2, and it only goes a half above and a half below. There. Okay, do you get it? This transformation idea is a very important thread in this IB course. Come down. What have we got? Here's our definition. The amplitude of a sine or cosine function is the size of that number in front. So even if we reflect it in the x-axis and put neg 2 there, it's the size of that 2 that will give us the amplitude. So let's do one here. So if I say here, there's sine x, and I'm going to draw neg 3 sine x, what's going to happen, there's two things here. Let's do this properly. There's sine x, and let's multiply, let's do neg. Sine x would reflect it in the x-axis, and then the 3 is going to make it go up to 3. Okay, so where's our and down to neg 3. Okay, so here's sine, and then our function's going to go right down to neg 3 and up to 3. So the amplitude is a maximum displacement from the mean position, if you like. Amplitude is 3, not neg 3. So it is multiplied by neg 3. The negative is, however, really showing the reflection in the x-axis. And then the other one is the actual number is showing you the size. So here it is, it's just the size of that number out in front, giving you the maximum deviation from the mean position. Are you getting it? We've seen a lot of this before in notion, but not with sine functions. Okay, we'll just come down here a bit and stop that flicking. So here we've got example 10. Waves are produced in a tank of water, and we're looking at this sort of modelling now. And here's the formula. We're saying they're going up and down, so it's like a sine or a cosine function. And there's our formula. And here's the graph. And can you see t here is in radians now? Because in practice it has to be a distance, not a degree, not a turning. Okay, so here we've got key points. That's a minimum and a maximum. And what we've got to do is find the value of k and the value of m. Well, I think what we could do first of all is try and do m. Let's see what they do with this as we come down and have a look at the answers here. The constant k is equivalent to d in the general form. What does that mean? Well, equivalent to our y translation. So how far up there have we gone to the mean position? Where is the mean position? So here it's, if you like, halfway between the maximum and the minimum y value. So you find the mean position, it's the mean of the max and the min to find that new line. So here it is, 7.4, somewhere in there. Not very well drawn there, mate. 7.4 y, so that's how much it's been moved up. That's what they're saying d in that original general form is represents a y translation 7.4. Now we want to find in our formula the m value, and just remember here, just go back up, the m value is this number here, which is what? The amplitude. Okay, so come down and let's have a look at the amplitude. How far above and below the mean position does it go? So here what we will do is find how far the maximum is away from 7.4. So 9.7 take 7.3 is 2.3. Or you could have 9.7 take 5.1 and divide by 2. Okay, either one. Or we could do that. Okay, so that's our function now. We've got 2.3 and 7.4 in those holes. So there's our function. And we could also evaluate this at one of the values and just check it. It checks out as being correct. What about the maximum and minimum values of this function, and see if we can find the period, how often it repeats itself? Okay, so if we have a look at this, we would say, okay, what are two values that occur at equivalent points? So if we say this, 8 and 9.7, and we can see here from the minimum to here, so what's the distance between those 2 points? Well, let's have a look. There's one period's worth, isn't it? Going here to there. So from there to there is one whole period or cycle of the function. And there would be another one. So at this point we're 1.5 cycles, 1.5 cycles if you like, or periods worth of this function. So what is its period? Well, 1.5 times its period is equal to, what's the difference between those two? Here, from there, hang on, where are we? There to there is 2 up to 8. So that's 8 units in the x direction. So 1.5 periods is 8 units. 2 up to 8, is 6 units. 2 to 8 is 6 units. It's 6 units here. That's 1.5 periods. So let's do, what will it be now? Let's get rid of that. So 1.5 periods is that. So if you multiply both sides by 2/3, you get a period is 4 along here, 4 units. Okay, so where would you expect this to be? We'd be expecting that to go from 2 to 10. 2 periods worth, from here 2 to 10. So we're starting to look at some properties of these functions now. Okay, so we'll build some skills here. We'll just have to keep concentrating on it now for a bit. Let's do some here with an interesting function like this. Alright, the most important thing though is to change this function into our standard form, which is a sine bx plus c plus d. So can you see it? That should be factored out. Okay, so when we do that we get this function here. It's a sine of 2 outside x plus pi on 3. We're going to take a common factor of 2 outside the bracket. This is very important to separate the effects of the changes on the function. So here, what are we going to say? Well, first of all, let's talk about the stretch. Here we've got a stretch in the x direction by a factor of 2. But if you multiply the x by 2, you get 2 cycles. So it's really more like people saying a shrink, but it's a stretch of a factor of a half. So this is an x stretch of a half. We did this before in other functions. So we're going to come to this line here. Alright, you're doubling every x value right up to 2 pi. You're going to get 2 cycles. 2 cycles in 2 pi now instead of 1. So it's actually a stretch of a half. It's a shrinkage if you like, but it's a stretch of a half. 2 cycles in 2 pi now. And then this in here, what's that represent? It's a neg pi on 3 translation. So we now have to move the blue one back pi on 3. So here, each point was that this maximum was at pi on 4 now, wasn't it? Because it was a stretch of a factor of a half. It usually is at pi on 2. There's usually our maximum, but it was stretched by a factor of half, so now that's back at pi on 4, and then we have to take pi on 3 away from it to get our new maximum point there. So everything's got to be moved back pi on 3. If you actually wanted to do this accurately, the easiest way is to choose a scale here in pi on 3s. Okay, so it looks like, pi on 6. Looks like that. So that the scale units would be pi on 6. Oh no, let's just get this a little bit right here. So let's get this right. So pi on 6 is unit, but we want to make it more accurate here. Like that. So this would be pi on 6. 2 pi on 6s is pi on 3, 3 pi on 6 is pi on 2, etc. That makes it easier to shift it by this, which would be 2 scale units, if you were trying to do it accurately. We generally aren't asked to do it quite like that in this course. This is called a phase shift. Well, that applies more to physics than to maths. Here we'd say simply it's an X translation of neg pi on 3. Let's go down and look at some more. Here we are. Period and horizontal translation, or phase shift if you want, of sine and cosine functions. Now, this is an interesting one. The X translation is the opposite sign to this, so it's neg c. And this number in here gives us the number of cycles, doesn't it? We multiply x by b, there will be b cycles now in 2 pi. So therefore the period, 1 cycle, will be equal to 2 pi divided by b. So remember this stretch here by a scale factor of a half produces more cycles. It's shrunk if you like. It means there's b cycles in 2 pi. Each x value you're multiplying by b and making it bigger before you find the sine or the cos of it. There's going to be more cycles. So both of them have a period equal to 2 pi divided by the number of cycles there, which is the b value. Okay, let's come down and look at one. Looks a bit different here. Here's a function that we have here, which has got some changes in it. You're looking at the graph now. And what are the changes you can see here? Well, we're saying, let's take the graph is of the form y equals a cos bx. Can we fill in some numbers? Well, first of all, write down. That's a command term in the standard level IB course, which means you should just be able to write down there's just a mark for the answer. You don't have to show any working. So what's the value of A? What is the maximum deviation from the mean position here? What is it? Well, it's up to 14. So A is 14. Can we see the period of this graph? Let's see how long it takes to repeat itself. Here's 1 period's worth to there. And then it's the same again. The period looks like it is pi on 4. So therefore, to find, here we are right over here, a cos bx, we've got that one. To find this value, we know this is a number of cycles. So the period is 2 pi over b, and we can see here it's pi on 4. Therefore, what can you do? Well, to get b, let's say 2 pi equals pi on 4 times b, multiplying both sides by b, and then dividing by pi on 4. This is best done particularly for the harder ones. So here, this comes to 8 pi on pi, right, division by a fraction. You invert and multiply, remember? So b would be 8. So if we put an 8 in there, this is the sort of graph we would get. It would be stretched by a scale factor of 1/8. So in other words, shrinking if you like. Okay, study that carefully. That's very, very important now. Okay, so how's it going with all of this? Come on down and see what you think. Okay, here we have another function. We're going to do the same thing again. Look at the amplitude. and look at the period. So b is a half, divide by a half is 4 pi. So this is stretched with a scale factor of 2 now. Okay, sketching the function, let's have a look out to 5 pi. We have to do the following transformations. First of all, a horizontal stretch by a factor of 2 here, and here that's going to be stretching out, and then a vertical stretch by a factor of 2. What one is that? That's going to be the number in front here. So we've got an amplitude here of 2 either way, and then it's gone down -3/2. So these are the key numbers here that we're trying to do. And what about the domain? Well, the domain for all these functions is going to be x is a member of R, isn't it? You can keep going around the unit circle. And then if you try to write this in terms of a range now, what's the range of this function? This time it's a little bit different. It's going up to a half and down to -7/2 here. And so what would the range be? The range would be -7/2 to a half. And how would you actually make this into a cos graph? Cos of x is the sine of x plus pi on 2, isn't it? Or in other words, any cos function can be written as a sine function with a phase shift. Because if you remember, sine is like this, and cos, we'll just dash it in there, is like this. There is a difference of pi on 2. So here, if you move sine back pi on 2, so that would be sine of x plus pi on 2. Remember the opposite sign there? Then you would get a cos function. Do you get it? You might have a look at this one in a bit more detail. Let's go on. And here we have it. Some results. If you move pi on 2, move sine x neg pi on 2, you get cos. Or if you do it this way, also putting in reverse, multiplying by a negative in there. If you have sine of pi on 2 take x, or that sine of neg x plus pi on 2. Okay, so sine of neg x is going to be reflection the y-axis, and then move it neg pi on 2. Could do that. Or if we took cos graph and shifted it plus pi on 2. That would do the same thing. So there are some interesting results here that are worth looking at. These two down the bottom are best thought of as if you have the sine of an angle. Let's take the sine of 30 is equivalent to the sine of pi on 2, or 90 minus 30. Oops, the cos of. So this is complementary angles here. Cos of 90 minus 30, or 60. Goes back to the old trigonometry approach, that if you have an angle in here, its sine, the opposite over the hypotenuse, is equivalent to the cosine of this angle here. So this is 90 minus theta, and the cosine of it becomes that over that, the adjacent over the hypotenuse. So these are the complementary angle results, complementary. The ones that add up to 90 have the opposite sine or cosine. Also true back in trigonometry land. All right, come on down a bit, see if we can do a bit more, this time with the tangent function. The tangent function is, of course, sine divided by cosine. Okay, and you remember that? The sine divided by the cosine, because the opposite and the adjacent, this is the hypotenuse, so the sine of theta was the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and way back, even in trigonometry land, if you look at the tan of theta, that's the opposite over the adjacent, which is exactly what you get if you put this one over this one. O over h, all divided by a over h, division by a fraction, invert and multiply, O over a, opposite over adjacent, which is the tangent. So it does work if we divide sine over cos, because sine over cos here will come that same ratio. And so let's have a look at how we get this graph and why it repeats itself with a period of pi. Come down and let's have a look. And here it is here. So as we go around here, you get unique values for sine over cos, sine x over cos x. Then in the next region, you're going to get the negatives of those, because sine is still positive, but cos is negative. So you get all these made negative. Then down in this quadrant, sine is negative and cos is negative. So sine over cos goes back and repeats the positive values from over here. And so on. In the next quadrant, sine is negative and cos is positive. So you're going to generate the same values but negative. So can you see it? As we go around, we're going to repeat that behaviour. All right, so let's have a look at some properties there. You can stretch it or shrink it, but the amplitude is undetermined, so because it becomes infinite. Sine x on cos x, as cos x tends to naught, this is tan x will tend to infinity, so it doesn't actually have any maximum value there. So that's the idea of this behaviour here, becoming infinite there for tan x. Alright, so no amplitude for that one. Its period is going to be pi. Here's some changes for tan. Same thing here. Tan 2x, a stretch by a factor of a half. All the angles are going to behave as twice as big. So you're going to get the first asymptotic value here at a half the original, which is going to be pi on 4. And so on. And so the period now is going to be pi on 2. It's going to repeat itself in pi on 2. Tan of 2 times x take pi on 4. Well, we need to then shift it by pi on 4. And therefore we're doing a horizontal or translation in the x direction. And so we're now shifting it across. So if we just compare those two, and I'll just go down more gradually here and see if we can compare those two. So we're shifting things across here by pi on 4. A little bit tricky here. But the period of tangent usually is pi. So when we have 2 in here, the period is going to be pi on 2. Because it's a stretch by a factor of a half. Come on down and let's have a look. Just make sure when you're doing this on your calculator, if you're drawing graphs on the calculator, if you're allowed to do that, like in paper 2, just remember, go to run mode, hit shift setup to go into shift menu, go into setup, scroll down and make sure it's in radians there. Make sure of that. Okay, that's if you're allowed to use a calculator to draw the graphs of these things. Let's go down and have a look at exercise 6.3. Now, without using a calculator, so you have to draw up your own scales and so on and try to measure this and plot these reasonably accurately on graph paper. Not a bad trick there. If you're looking at these common angles, just remember that we could do pi on 6, pi on 3 and pi on 2 are equal divisions there, and that's not a bad unit. 2 squares for pi on 6, 4 squared for pi on 3, etc. That's not bad. Okay, pause the presentation, have a go. The answers are right down the bottom. We'll come to those in a minute. Let's have a look at the next few questions, 13 and 14. 15. 16. Okay, study them carefully there. Here have some answers. Question 1 and 2. 3 and 4. 5 and 6. 7 and 8. 9 there. We'll just come down, have a look at 10, 11, 12, 13 and 14 there, and 15, we'll just sneak it in I think, 15 and 16. So, can you see we're doing all the transformations to every function we come across, and the sine and cosine ones are quite interesting in their periodic nature. Okay, study that well, it's an important thread, and we'll get into some more work with circular functions in the next presentation. At the moment, it's cheers from me.